Hey, what's up YouTube? It's been a while, I hope you're doing well. Today I'm going to demonstrate a new blueprint tool I've been working on for several weeks now. A tool that allows you to procedurally generate great looking waterfalls. It's packed with tons of features, and as usual, on top of a demo, I'll also do a long and very technical deep dive into this tool's inner workings. I also want to point out that I was hugely inspired by this game developer's own little experiment. I thought it was a super cool idea, so give that guy a follow. Alright, there's so much to say, so let's not waste any time and jump right into it. This waterfall tool is an editor utility widget, so just have to right click on that asset and click run. Next, it asks for a blueprint, specifically that one, waterfall_spline. So I'm going to drag one into the scene and select it here. Now there are quite a few settings I can play with to tweak the waterfall simulation, and for the most part it should be quite straightforward. Here's the amount of particles to simulate, the distance a particle may trace to be right away projected onto the nearest surface, and if projected, how offset it should be from that surface. Finally, how much of that projection to apply in a 0 to 1 range. Next, that min and max range is to fine-tune where precisely particles are spawned along that spline. I may also choose to spawn one single particle, at which point I may no longer specify a range, but a precise position along the spline. I can also choose to add a bit of randomness to that position. Same with multiple particles, right? Notice those two widgets spreading apart, the more randomness I add. Lifetime in seconds is sort of a security feature in case particles get stuck somewhere and don't reach the kill floor, so the simulation eventually stops sooner or later, right? Speaking of kill floor, this box volume acts as a way to specify the water level, so particles die when they reach it. You're free to use multiple boxes because you're also free to use multiple spline components to work on multiple waterfalls at the same time. Very cool. So maybe one here and maybe one there at a different altitude. Note that these position and range parameters are now quote-unquote spread over those two splines. So I can for instance choose to spawn a single particle anywhere on any spline. Sweet! Speed, max speed, speed randomization and flip direction should all sound quite straightforward, as well as gravity, bounce, drag and friction. Flow, however, is a bit unique. This is not physically based at all and has a few downsides I'll be able to explain during the breakdown, but this may somewhat help mimic a fluid behavior. A particle can be influenced by nearby particles to some degree, like be repulsed by them or match their movement direction. Next, obstacle deviation and repulsion, same thing, quite a cheap hack to try and mimic a fluid behavior, or at least try to deviate from a simulation that may look like rigid bouncing balls. Meaning a particle may trace forward and foresee collisions ahead of time. So this is going to deflect a particle away from incoming obstacles, and this slows down a particle ahead of time before it's about to collide. Now the trace distance is based on the particle's velocity, meaning the faster it goes, the further it's able to foresee obstacles. So this multiplier fine-tunes how that velocity affects the trace distance, right? And if that all sounds confusing, all these parameters have tooltips that should explain it a bit better. Finally, some advanced settings, that's how many simulation ticks to perform per tick. One means it's real time, right? But then it takes a while for the simulation to be done, so incrementing this speeds up the process. But too much and the editor can chug quite unpleasantly. It's all done in blueprints, so it's quite heavy for the CPU. This is by far the most costly feature, so disabling it can lead to quite a massive performance boost in case you have issues with that. Next, there's the simulation delta time, unlikely to be changed to be honest. And the trace channel for collisions, which is by default the visibility channel. Cool, so let's run a first simulation with say 10 particles to begin with. Note that this can be an iterative process. I can keep on simulating new particles, which means I can very well spawn one particle at a time, maybe one here, then one there, you get the idea. It's personally my preferred way, it lets me have the most control over the simulation, but you do you. So, toying with these settings can lead to quite dramatic effects. Something that looks a lot like bouncing balls, or something that looks like slow leaking water, or something that looks more like a typical waterfall. Alright, so each simulated particle leaves a trail behind it and creates what I called a path. So I can remove one if I'm unhappy with what the simulation has produced. By default, this index is always set to the latest simulated path, so it's quite fast to iterate, right? Like simulate one single particle, not liking the result? Well, delete, simulate again, delete, simulate, you get the idea. But I may also delete any path, really. Note that in order to see this path, the game view must be disabled. Okay, overall the simulation should be a pretty straightforward process, but there are a couple of things I should mention. First, it's most likely unnecessary to simulate lots of particles. It may result in too many vertices, too much overdraw, or both. Although the simulation might chuck quite hard with many particles, partially because of this flow feature. The more path, the more CPU intensive the simulation gets, so don't go crazy with the amount of particles. This tool is really not meant to simulate hundreds of them, and it's likely you don't need a lot anyway. Last point I should mention, particles trace against complex collision, so it may perform really badly with lots of triangles. I'd recommend building a proxy collision mesh if this is an issue. That way you can even cheat a bit and nudge the simulation in a certain direction, right? It can only do so much on its own, sometimes the collision must be tweaked in order to get the desired result. Alright, once the simulation is done and I'm happy with the result, time to generate meshes, and that happens in the Geometry tab. Here I can generate 5 types of meshes. There's this sort of flat plane mesh, one for each path. Same thing but on the other axis, does that make sense? Then there's this global mesh thingy, I'll explain this in greater details in a second. There are FXs, still just meshes, no particle system involved. And finally there are splashes. They all have their own settings, but they all also share common settings here. There are a few exceptions, so feel free to read the tooltips for extra information. So right away I want to point out that this mesh generation process can be an iterative process, just like the simulation process can be. Meaning I can build meshes layer by layer, path by path, if I wish to do so. And there are 3 features that allow this. The first one is this custom path selection. It works with a range, so from say that one to that one. Let's assume I first want to generate meshes for those few paths, maybe that thick. Now let's generate meshes for the remaining path, maybe a bit thinner this time, why not? Oh wait, the previous mesh disappeared. Well, that's intended. That way I can tweak settings and keep iterating on the same mesh very easily. Like, is it wide enough? No? Well, no worries, increase this, click generate again, and boom. Maybe tweak that as well, click generate, and so on, right? I don't have to delete that mesh every single time. Which means that once I'm done with it, I need to freeze it, and only then I can generate a new mesh. Just have to be aware that I can now generate the same exact mesh in case I don't change any of these parameters, so gotta pay attention to that. Also, there's no undo system, which means if I need to go back and tweak the mesh I just froze, well, it's not really possible. I could delete all meshes and restart from scratch, which isn't ideal, but it's a possibility. Or, because each frozen mesh is for now, emphasizing on for now, an individual actor, I can manually get rid of it and regenerate it. One of the features that allows an iterative workflow when generating meshes is the ability to go back and forth between the Geometry and Simulation tab. Meaning, I could simulate a couple of paths over here, generate meshes, and freeze. Clear path, simulate a bunch of new paths over there, generate meshes, freeze, and so on. So the tool is quite permissive and I feel like it allows you to work in a lot of different ways. Here's another even cooler example. I could first simulate a bunch of paths and generate meshes, duplicate that waterfall underscore spline actor and maybe tweak its splines, select it here, make sure paths are cleared, simulate new path, and generate meshes, and voila. I can go back and forth between multiple actors and multiple splines and work on a single unified mesh for multiple waterfalls at the same time. Super cool. Also, one more thing, by default, the static mesh this tool is going to generate is going to share the same transform than this spline actor, so same location, rotation and scale. However, you can select any other actor and use its transform instead. Note that as soon as a mesh is generated, the origin is locked, so it can no longer be changed. The reason for this is a bit technical and I won't bore you with the details, but yeah, make sure you have the origin where you want it to be before proceeding forward. Alright, now that's out of the way, let's actually see what these settings do. Those two settings are quite cool and let you remap each path in a 0 to 1 range. That could be useful to add extra layers at the top or the bottom and whatnot. Segment length is quite important and controls the amount of subdivisions. Force include hits does what it says. Collisions generate hit points that can be included to generate extra vertices where it could be important to do so. However, a particle may, say, slide against a surface and generate tons of consecutive hits, and thus lots of vertices, right? So this force include hits feature can be fine-tuned and controlled with this hit force parameter, to only include strong enough hits and filter out undesired ones. Next, smoothness is quite straightforward. Smoothing positions result in a, well, smoother path. That's kinda dependent on the amount of points, so the fewer points the stronger the effect, so that's something to keep in mind. Smoothing tangents, that's useful for paths that change direction quite suddenly, like upon collisions, which may result in the mesh twisting in all sorts of weird ways. And smoothing tangents can help with that. Smoothing normals, well, same thing, but for the mesh normals. It won't affect the way meshes are generated per se, and this only has a very subtle effect, to be honest. Next, turbulence. That's a value stored in Vertex color in the alpha channel. Turbulence doesn't have any impact on the simulation or the way meshes are generated. It's just a value that may be useful to have to create more intricate shaders. Basically, there are three things that participate in the turbulence: collisions or hits, obstacle avoidance and repulsion, and flow alignment and repulsion. The turbulence value can be propagated upstream or downstream or both with these two settings in centimeters. And to illustrate this, I'm going to use the debug turbulence material and disable upstream and downstream propagation and flow and obstacle weights as well. Next, I'm going to tweak this max hit value to remap hit forces to a 0 to 1 range. See, I can increase the way hits participate in the turbulence by lowering this threshold. I can also include points that were killed by kill floors, and they should have the maximum hit force because they likely had the maximum velocity at that time. I can also go to the debug tab, change the mode to single point and select cache points to see what's going on. See, it says turbulence is 1 at that last point. By the way, this debug tab has tons of options. It mostly helped me during development, to be honest. I don't expect it to be that useful during production, but who knows. Now I'm going to spread turbulence upstream by, let's say, 5 meters. Regenerate meshes, and that turbulence has indeed been propagated upstream. Same with downstream, cool. Then let's have the flow and obstacle deviation participate in the turbulence a bit as well, and voila. So this turbulence value is essentially a very fake way to create areas in the mesh where technically, I suppose, there should be some turbulence in the flow, right? Either due to water colliding against obstacles, being deviated from obstacles, or colliding with itself. I personally did not use this in the shaders I provided, but I reckon it may be useful to push the visuals to the next level. It's up to you really, and again, this turbulence thingy has no effect on the mesh itself or the simulation. Cool, moving on, normals. Autocompute is straightforward. If true, no setting here will have any effect at all. Geometry scripting will compute ground truth normals. But most often it can be quite handy to have artistic control over the normals, so I'd say this should be false most of the time. At which point you can choose to tweak normals in a few different ways. First, Tubify is quite interesting. Rather than having normals point along the path up vector, they diverge and point to either side. That will result in that flat mesh having a rounded look when lit. Override is straightforward as well. I can specify a normal direction and voila. And finally, I can have the last vertices match the water plane Z normal up to a certain distance. I personally didn't use this, but it might help you get a smoother transition with the water depending on your shader, but it can also make the mesh be lit quite bizarrely, so again it's something to experiment with, I suppose, you do you. Next, Trace simply tries to nudge vertices away from penetration, or the other way around, project them onto the nearest surface, or both. It has a few downsides, like see, this vertex could trace far enough to be nudged away from that penetration, but not that vertex below it, resulting in an ugly stair-stepping effect, not great. Maybe useful still, and you can even do weird things like project to end traces and have that kind of sticky mesh. Could be used to mimic surface tension and water sticking to surfaces and whatnot, not sure you'd want that, but oh well, it's possible. Next, offset simply pushes vertices along the up vector, and that may help prevent some clipping, and I can fine-tune where that offset happens along the path using a curve. So probably none at first to ensure the waterfall mesh stays flush with the river mesh, right? Bulge is similar but only really affects certain types of meshes, like that one, if it has subdivisions. It's used to push middle vertices either outward or inward. The bulge profile can be tweaked, as well as the bulge amount along the length. Bulge also affects where cross meshes are generated from, so they actually cross the flat mesh at the correct location, if that makes sense. Plus it has an effect on the splash mesh as well, so its curvature matches the flat mesh's curvature. Finally, there's a UV scale setting, nothing fancy. So that's most of the common settings, onto the mesh generations then. This type of mesh you're already familiar with, and most of these settings are quite straightforward, I don't need to explain much. That curve, for instance, can be used to fine-tune the width along the length, maybe have the mesh be thinner at the top or something. Moving on, spline roll allows vertices to match the spline slope if it has any, else vertices are flattened on the z-axis. Next, there's what I call the cross mesh, and you've already seen it as well. Settings are also quite straightforward. That offset is in a -1 to 1 range to push the cross mesh in and out by its entire width. -1 completely inside, 1 outside, and 0 right in the middle. Finally, align normal ensures normals point towards the up vector, which drastically helps smooth the look when lit. The only downside of tweaking normals like so is that usually with flat planes, a common trick is to use the vertex normal and camera vector to create some kind of fade out when looking at it from the side. And that can be quite problematic to do when normals are not pointing the way you expect, so that's a trade-off. Next, there's what I call the global mesh. Now, it's a bit of a tricky one because it comes with a few caveats, but I still think it can be quite handy, especially to generate LODs. Speaking of LODs, this tool cannot generate LODs per se, but I could still generate different meshes and create different assets and recombine them in my favorite 3D software to ultimately create LODs. So generating LODs is possible, I suppose, but definitely requires extra manual steps. Anyway, a global mesh is a mesh that tries to connect every single point of every single path, and that can be quite problematic. For instance, I may have multiple splines, and so generating a global mesh may obviously lead to this mess. Fortunately, using the path selection feature solves this issue, right? Next, bigger issue, a path may end prematurely because a particle may get stuck somewhere or something, right? And that will result in this kind of mess. So it's recommended to ensure that all paths do indeed reach the water in order to use this global mesh feature. But even then it can cause issues. First, a path may cross another and that can result in a weird mesh. Second, even though all paths reach the water, some may be longer, because of obstacles along the way, right? So some may have more points, or vertices, I may say, than others, which may be problematic. It may skew the mesh and lead to UVs being quite drastically stretched, because the algorithm I use to build that mesh is quite naive. So I'd say this global mesh thingy can be very useful, as long as you're aware of its limitations. Again, I feel like it could be very useful to generate LODs, so maybe have one path here, one there, and create a global mesh, and voila, that could be your LOD 2 or 3, right? But it could also be used on top of other meshes to add an extra layer and some more depth to the waterfall. Anyway, moving on, this expand parameter pushes vertices to either side. It could be very handy in case there's a need to fill holes on the sides or have the global mesh cover more area or something like that. There's also this neat override subdivision feature. Basically, this is a kind of geometry you can expect without it and with it. It lets me specify a fixed number of subdivisions along the y-axis, but also on the x-axis. Thus, vertices will be generated in between paths, either using a linear interpolation or a cubic interpolation to create some curvature. Quite neat. Now, a quick word about UVs and vertex color. All meshes but FX meshes have 4 UV maps. Yeah, that's a lot, it has a memory cost for sure, but it's not that bad and it's super useful. The first UV map is a normalized 0 to 1 UV map, quite basic. The second UV map is pretty much the same thing but in centimeters. That may be very handy to create distance-based gradients that are independent of the path length and things like that. The third UV map U channel contains a random 0 to 1 value per path. Useful to offset time and randomize parameters and things like that, so no two paths look alike. In the V channel is a 0 to 1 position value relative to the spline that path spawned on. Could be useful to create a bilinear gradient and build some kind of fade out at each side. Finally, the fourth UV map contains speed in centimeters per second in the U-axis and what I call the flow in the V-axis. Flow is basically a stack of inverse speed, so the greater the speed, the less UV coverage, leading to textures being stretched, the faster the water flows, which is super handy when scrolling a texture to convey a sense of speed and acceleration, but more on that during the technical breakdown. Finally, the flow direction is encoded in vertex color in RGB. Note that it needs to be remapped to a -1 range, like so, and turbulence is stored in the alpha channel. So you get access to all kind of very useful data you can exploit in all sort of ways in shaders. Alright, moving on. FXs, oh boy. This doesn't rely on a particle system, it's still all based on meshes, and I'll demonstrate how it works later on in the video. Now, this technique obviously doesn't allow as much user and artistic control as using a particle system like Niagara, but I reckon it's good enough and possibly quite a lot cheaper. So, for each path I can spawn a number of particles. Now, these are just simple quads, see? So each can be randomly rotated in U. And most often you'll want to use a shader to turn these quads into camera-facing billboards. And if so, this should be set to 1 to make them face towards -z. It simplifies the process, but more on that later on. If, however, this is set to 0, particles are randomly rotated. I can also subdivide them in X and Y, and that could be useful for many things. For instance, you could compute lighting per vertex, and so having extra vertices could be great. Also, once subdivided, particles can be rounded, and that may help to reduce overdraw. Particles can also be circles rather than rounded quads, at which points UVs are circular as well. That could be useful on rare occasions, but most of the time quads without subdivisions should do the trick. Size is straightforward, pivot should be as well if you ever used Niagara. It just offsets the pivot point, which may change the billboard's camera-facing behavior and other things. Next, those spread parameters let me randomize particles' positions along the path right and forward vector. And then there are a bunch of filters, like say filter by distance to water and so on. They should all sound quite straightforward. The one thing to be aware of is that you can very well set up filters in a way that doesn't create any particles at all. Like say use a first filter by distance in centimeters to only spawn particles the first few hundred centimeters or something, but also use a second filter by normalized distance to only spawn particles at the very end. That doesn't make any sense, right? There's no overlapping regions, if I may say, so no particles are spawned. And this tool kinda fails to provide meaningful feedback regarding those filters, something that could be improved, but oh well. I can also scale particles up or down based on certain criteria as well. Let's say scale particles down to 0 if the normalized distance is 0, and there you go. I can even remap that normalized distance, invert it, you get the idea. It's quite a permissive tool, so I feel like you can really go nuts. Finally, there are what I called splash meshes. These are meant to work with those flat meshes. See, it's a perfect match. And to create a perfect match, they take into account the bulge, and also that other mesh subdivision parameter, unless you override it here. Most of these other settings should be quite straightforward for the most part. Front radius, back radius, segments along the length, I suppose, segments for the end caps. That's the way vertices are distributed along the length, maybe more closely to the center or to the outer edge. And same but for UVs. Voila, that's quite a lot of information to digest already, so let's take a breather and have a look at how I'd use this tool to create a waterfall for this small scene. Again, this is just an example, one that I suppose works best with the shaders I provided, but you're free to build your own shaders and do things your own way. First, I'm going to spend some time simulating paths and making sure I have what I'm looking for. Not too many, just enough with interesting shapes. Okay, that looks good, let's move on. I like to first generate a global mesh. It's a bit easier to work with when there's nothing else going on. And I like to slightly offset it along the normal to give some extra volume to the waterfall. Next, I'm going to override subdivisions and also ensure there's nothing crazy going on. Again, that global mesh feature is a bit finicky to work with, so gotta be cautious. Alright, maybe toy with expand setting a bit, why not? That's a bit too much. Still slightly too much. Alright, good. Now the base mesh. I'm first going to use a negative offset because I'm also going to increase the bulge. And let's bump up the subdivisions to 6. Also maybe add a tiny bit more vertices, why not? Next gen, am I right? Maybe tweak the thickness a bit? That's probably a bit much. I might have simulated too many paths for meshes that thick. But that's too thin though. Let's see, that's still too thin up there. Yeah, I don't know, maybe. Alright, let's go with that. Next, the cross mesh. Increase the thickness by some amount. Maybe even push the mesh forward a bit. Okay. Then splashes. Now they may look a bit wide by default because I match the base mesh thickness, and obviously with transparency it doesn't look as thick as the mesh really is. So I'm going to shrink those splashes by some amount, and then quite drastically increase the front and back radii. Alright, maybe add a bit more subdivisions, so the shader has more vertices to play with for the world position offset logic. Yep, okay. Now, FXs, that's the tricky part. Let's first use this material to generate quite a few medium-sized particles. Now, this material expects billboards, so let's make sure that is set to 1, randomize U as well, and align normal too. Then add one subdivision in X and Y to make those quads round and reduce overdraw a bit. Maybe increase that and the count as well. Now these are a bit hard to see right now, so I like to switch to a debug material at times to see what I'm working with. Oof, that's a lot. Now, I don't really need to spawn particles right at the water level if they are meant to fall, right? So let's add a filter by distance to water to get rid of those unnecessary particles. And maybe have them be thicker at the bottom. And although I don't like them spawning so early. So add a filter by distance, okay. And maybe scale particles down at first as well. Alright, let's switch back to the drips material. Increase count again. Let's fly around for a bit to see how I feel. It could be decent enough, I don't know. Let's see, maybe push particles forward a bit so they are more visible. Maybe a bit too large still. What if I increase that spread in X though? Oof, a bit much. Alright, good enough. Let's freeze that mesh and add some more particles. So I'm going to switch material and use this splash material. Now it does not expect billboards, so let's turn that off, and it needs unmodified normals, so let's turn that off as well. Next, let's use a filter by distance to water to spawn these splashes right at the water surface. Okay, let's try. I don't see anything. Maybe time to switch to a debug material again. Okay, they are definitely where they need to be. Oh, actually, let's kill that spread in Y. And also, let's push those particles slightly up, like so. Even more, maybe? Alright, increase the size, and let's try again. What's going on? Oh, I'm dumb. That's the wrong material. That should be splash underscore water. Ah, much better. They are possibly too high now though. And too big maybe. Let's push them forward. Yep, okay, I'm fine with that. Let's see how it reacts to the lighting. Yeah, decent. Let's take a second because again there's no undo system, but yeah, that looks decent to me. Alright, so let's freeze that. Now let's add some mist at the water level. That doesn't look too great. Increase the size and lower the count a bit. Oh, actually they are not spawned at the water level yet. Oh, and I forgot this material needs billboards. Much better. And so the way mist rises is controlled in the material instance. Cool. It's a bit too visible though to my taste, so let's push mist a bit inward. Alright. Mist is a bit sketchy, to be honest. Definitely could be improved and has a few issues with lighting, but it's a starting point, I suppose. Alright, that looks good to me. Now, for the most important part, this waterfall is for now just still made of multiple temporary actors. So the next and final step is to bake them all into one single static mesh. And that's super easy to do, specify a path and an asset name. Now please note that this is going to erase any existing static mesh assets, so double check that. Click that button, wait a bit, and voila! All temporary actors have been deleted and replaced with one single static mesh actor that points to that one single static mesh asset. Awesome! Now you may see those splashes falling below the water level, and you probably want to avoid that. So these material instances have a switch you can enable to let you specify the water height in wall space and mask particles underneath the water. And that's it. The only bit I'm unhappy with regarding this tool is the way affixes are created. You have to juggle between quite a few materials and settings, and it gets confusing real fast, but I'll provide a documentation so you can easily replicate my workflow. Last feature I want to showcase, an experimental one I might say. You may not like this mesh-based particle system. Maybe you'd prefer using Niagara instead. Well, I built a feature that may give you, let's say, a starting point. It's not amazing by any means, because it really wasn't my priority to be honest, but basically if I go to this FX tab, I can sample a bunch of points here and there and bake those points' positions and velocities into two textures. Textures I can then sample in Niagara to generate particles along each path with an initial velocity that matches the simulation. Now this doesn't look that great because this Niagara system is really just a template to show you how these two textures are sampled, so feel free to tweak it to your likings. Alright, that's my waterfall tool. I'm quite happy with it, to be honest. There are things that could be improved, but I spent close to 8 weeks working on it pretty much full time, so yep, it's really time to move on. Now this tool is bundled with tons of cool tech, so let's get technical and see how it was built, shall we? And buckle up, because oh boy, there's a lot to say. Alright, it all starts with an editor utility widget. It's a special kind of widget you can call in editor, and it offers a few interesting features. Namely a tick in editor, very useful, and view property widgets, which are very handy. Just have to drag one here, call that function on preconstruct and forward self. Then create a variable and have that view property widget point to it, and that's it. It creates this widget to tweak this variable just like you would do anywhere else in the engine. And that view property widget has an event you can listen to be notified when this variable is updated. This is however a bit finicky to work with. It doesn't trigger when updating vectors, float intervals and so many other types of variables. It's a bit unfortunate, but for floats, integers and most simple variables types, it's fine. Okay, so that's what this widget is mostly made of, view property widgets. When some are updated, I enable or disable other view property widgets, like say, hey, is that distance 0? Then this feature has no effect, so disable these. Nothing too fancy, to be honest. See, most don't do anything at all. I also built tabs and collapsible panels. Those are quite simple as well. Tabs are made of buttons. Upon clicking on them, I simply enable the tab button I'm quote-unquote exiting and disable the one I'm clicking on. Then I use the widget switcher to create different menus, and so I update that switcher's active index to, well, simply switch tabs, and that's it. Same for panels, quite simple. They are made of a button and most often a vertical box. Each button has a text and an icon. Upon clicking on that button, I simply switch icon and update the vertical box visibility, and that's it. Here's a collapsible panel. So that's the gist of it really. There's not much more going on in this utility widget, at least regarding the interface. It's all about patience and building a crap ton of view property widgets and making sure the interface looks decent, is readable, and functional, which can be very time consuming. Now, using an editor utility widget is usually my go-to strategy when I want to have a tick in editor. See, this tick event is right away firing as soon as I run this utility widget. So it's constrained by this processing boolean, right? So the tool can idle and not call any function. And that boolean is turned on when either running a simulation, generating meshes, baking FX textures, or drawing the debug view. Let's focus on the simulation part for now. So let's assume the user clicks this button to run a simulation. That click event is fired and calls this start simulate function. In here, basically, for each particle to simulate, I call this createPath function, but more on that in a second. That variable, by the way, is the one this viewProperty widget modifies, right? So paths are created and added to this path to process stack. Then that processing boolean is set to true. Most of the widget is then disabled to prevent the user from being able to further click on buttons, tweak parameters, and break everything pretty much. That enum is also set to simulate, so that next tick, this update simulate function is called. It isn't a complex function. Basically, while there's a path on the processing stack, and while this hasn't been called too many times this frame, get the first path on that stack and call it simulatePath function. This simulation iteration variable is passed to this function as a reference, so it's actually incremented within that function. And that again prevents this loop from being called too many times in a single frame, depending on this batch setting. This is to prevent the editor from chugging quite hard and to spread the simulation work over multiple frames, because again it's quite CPU intensive. Anyway, if simulated, remove that path from the stack, and if there's no more path to process anymore, I called endSimulate. In here, I double check path to process where indeed all correctly simulated. User might have cancelled the simulation, who knows. And so if all were not simulated, destroy them all just to be on the safe side. But if all were, they still need to be what I called registered. More on that in a second. At that point, the tool can stop ticking and be back in an idle state, so I clear those processing arrays and re-enable the widget. And that's a very broad overview of how the simulation is handled in this editor utility widget. Now let's dive a bit deeper, because there are obviously some missing pieces still. There are those createPath, simulatePath, and registerPath functions that, you guessed it, do the heavy lifting. Let's start at the beginning and check this createPath function. First, I generate a 0 to 1 position value. If spawning multiple particles, and thus multiple paths, that value is first based on the path index and amount of paths, so it's 0 for the first pass and 1 for the last one. It's then remapped based on those min and max parameters I explained during the demo. So 0 may become, I don't know, 0.25 and 1 may become 0.75. That's how that spline range feature works in a nutshell. However, if spawning a single particle, there's no need for that, and I just use that one parameter. Parameters that once again this viewProperty widget points to. And same with these two variables. Okay, now this waterfall tool allows the user to work on multiple spline components. So this 0 to 1 value is essentially a position somewhere on a spline, but on which spline and thus where exactly on that spline. And in order to know that, I first loop through all spline components and compute a list of distances, I'd say. So 0 at first, then if the first spline component has a length of 500, 0 plus 500, and so on and so on. And that also lets me have the overall distance in centimeters, which lets me convert this 0 to 1 value into a global position in centimeters. Say 0.75, if the overall distance is 1k centimeters, that'd be 750 centimeters. So next, I just need to march forward by that distance and see on which spline I end up at. Then, knowing the distance at the start of the spline and the spline length, I can remap this value into a position in centimeters relative to this spline, and thus into a normalized 0 to 1 value as well. And that's the value I shall use to sample a transform on that spline. So in blueprints, it translates to this. I first loop through spline components and compute the list of distances and the overall distance. Next, convert that 0 to 1 value to centimeters. See on which spline that distance is by marching forward. Next, remap that position in centimeters to a position relative to this spline, still in centimeters, and then normalize it. And finally, using that last normalized value, I sample a transform on that spline. Note that this constant velocity option must be enabled because busy splines are a bit weird. A 0 to 1 normalized distance doesn't actually translate to a 0 to 1 time, unless you take extra steps like UI does with this constant velocity option. Next, using that transform, I spawn a waterfall path blueprint actor. And that blueprint has a few variables exposed on spawn, so I can forward these values if later needed, and most importantly, self. It means that this blueprint, as soon as it's spawned, has a reference to this editor utility widget, and thus has access to all of its public variables, meaning all of its settings. Which is very handy, like right away in that actor's initiate simulation function. I get the tool spawn trace distance and offset variables, these in the interface, to right away project that actor's initial position onto the nearest surface if desired. Next, get the tool's various speed settings to compute an initial speed, to then create and inject a first initial point into the simulation. At that point the simulation is ready to go, so time to investigate that simulate path function then. This function isn't part of this widget, but a part of this path actor. Now, a word about this actor. I went back and forth a billion times before settling on using an actor. At first, a quote-unquote path was a struct, but that struct needed to contain arrays of structs, vectors, and so on. So I had arrays of structs within arrays of structs, which in my opinion can be unstable and a nightmare to deal with in blueprints. Hence why I switched from structs to UObjects. But then UObjects lack a world context. So some functions, as far as I know, are not available in UObjects, namely trace and debug functions, which can be quite constraining. Constraining enough that at one point I decided to finally move away from using UObjects and settle on using plain simple actors. And that process was painful. Refactoring blueprints isn't super fun nor fast, but oh well, sometimes you kinda run in circles for a while until you find the right architecture. So each path is an individual actor, which can clutter the outliner a bit, but that's not too bad, they are clean once you quit the tool. Each have a list of simulated points, and a simulated point is a struct containing a few variables, position, velocity, and so on. So a quote-unquote simulation, as far as this path actor is concerned, is really just a sequential list of points. And that array contains at first an initial point, right? The one added during that createPath function. So naturally it all starts with that initial point. In this simulatePath function, I get the latest simulated point, so at first that initial point, and save it in a global variable, so I can iterate on it more easily. A bit dirty, but whatever. Then while the simulation hasn't ticked too many times yet, I cache that point in a local variable before I iterate on it. Next, this apply movement function simply adds gravity times delta time to the velocity. Here I apply the max speed limit, and then I apply drag, which simply scales down the velocity based on this drag value and delta time. The higher the drag, the closer this gets to 0, and thus the more the velocity is scaled down. Once velocity is computed, I apply it. Now, the idea of adding the average of the previous and new velocity can sound a bit weird at first, but this is the Verlet midpoint integration method. It's quite common and is what UI does for most, if not all, of its gravity-accelerated motion, including the character movement component. There are plenty of videos on Verlet physics, so feel free to investigate it on your own. Anyway, at this point I have this particle's initial position, its updated velocity, and the position it should have at the end of this frame. However, there might be obstacles along the way, or water, what I also internally called kill floors. So let's check for kill floors first. This array is a list of all box volume components this actor owns. Now I could get the particle's new position and simply check if it's inside any of these boxes, but that's not a great approach. A particle's delta movement could be large enough that it could pass through a thin enough box during a single frame. Unlikely to happen, but you never know, why not do things the right way? So a better solution would be to check if the particle goes through one of these boxes, kinda like line traces. And I could, I guess, use line traces, but then I'd probably have to use custom trace channels to ensure that I only trace against these boxes, or something similar. It could be annoying to set up honestly. So meh, why not do this myself? And actually, this geometry scripting's ray box intersection test node does most of the heavy lifting anyway. I get the movement distance and direction, create a ray that starts at the previous position, check if it intersects with that box, and if so, that's a successful ray box intersection test. but actually I want a segment box intersection test. So I just check if the hit distance is smaller than the intended travel distance, and if true, it means this particle is going through that box. So get the actual hit position and do things the right way and lerp the exact velocity at that position. Then flag that particle as killed and compute the hit force. If killed, there's not much else to do. I just increment the distance traveled, and then update the particle's age, which might end its life. At this point I'm done iterating on this particle, so it's ready to be added to the simulation, and it's as easy as incrementing this particle stack. Finally, I check if the particle is still alive, and if it's dead, then the simulation should definitely end right here, right now. So flag this path as simulated and return true, which in turn, remember, will remove that path from the processing stack and move on to another path next tick if there's still any to simulate, right? Now that's in case the particle went through a kill floor. If not, well, time to check for collisions. Now I went a bit overboard with this function, but I wanted to illustrate an important concept, several concepts actually, but you could go with a much simpler setup. I wanted to showcase what's commonly called substepping. This is essentially the same exact technique used for the character movement component. It has the concept of a remaining delta time and iteration count. But what does it mean? Alright, let's assume this particle starts here. Gravity is added, velocity is applied, and so that particle should have this position at the end of this frame. That's 100% of its intended movement, right? Or let's say one entire delta time worth of movement. If the game is running at 60 FPS, that'd be how much movement to apply in around 16 milliseconds. Now, let's assume there's an obstacle right here in the middle. This particle now can travel no further than half of its intended movement. And the million-dollar question is, what happens to the other half? The naive approach would be to stop here for this frame and continue next tick. But that's not so great. Let's say this particle is actually your character's capsule component. It was falling and hit something along the way, not there, but right here. Thus, let's say 99% of its intended movement is prohibited by this obstacle. And so the character would pretty much freeze for one single frame, something you'd definitely feel as a player. To avoid that, what's remaining of the intended movement must be applied the very same frame. And this must happen in some kind of loop, right? Because you could apply the remaining movement once, naively I'd say, but then what happens if there's actually a second obstacle here? You kinda see that we have no idea how many deflections we might need to do in order to apply the entire movement, and thus why a loop is in order. And that can be called substepping. And again, the character movement component uses substepping. For instance, if falling and a ground is hit, it transitions to the ground state and applies what's remaining of the delta movement in the ground state. Ground states that may need to further deflect from incoming obstacles along the remaining movement the very same frame. So one quote-unquote single movement could very well be a cascade of multiple smaller movements, all deflected in all kind of directions. And that's one of the principles behind substepping. It's not its only use, but for today let's keep it somewhat simple. Alright, let's check how this principle is translated to blueprints. Here I assume there's at first one entire tick worth of movement, and I perform a loop while there's any movement to consume still. Next, I trace from where the particle comes from to its target position. If there's no hit, and if that's the first iteration, then there for sure was no hit at all. So flag the particle as airborne, its entire delta movement was consumed, return. However, if there's a hit, things get complicated. First, I store the hit normal and compute the hit force. Next, if the previous simulated point hit something, and the hit normal is almost identical to this new hit normal, it most likely means the particle is sliding against the same surface. Next, I get what I call the projected direction. That's the velocity projected onto the hit normal and normalized if not null once projected. Because, for instance, a particle might fall straight down onto a planar surface, resulting in a projected vector that is indeed null. In that case, I generate a random unit vector around the hit normal. Note that this isn't physically based, it just better mimics a fluid behavior, I suppose, that ensures the quote-unquote fluid particle has always a direction to go when deflected. Cool, once that direction is computed, I get the speed along that direction, multiplied by the delta time and some friction value. Subtract this to the velocity to essentially brake along that projected direction, and that's the friction mechanism. However, because it's a subtract, I double check I didn't go in reverse in case the previous velocity was small enough or friction large enough. At that point, movement speed is set, and it's just a matter of choosing a direction to go to after that hit. And I either use a mirror-like reflection vector or the projected direction based on that bound setting. Finally, check the speed, and if too small, consider this particle stalled and stop the loop. Else, well, there's still an issue at play. There was a hit, right? So I need to apply that particle's remaining movement along the deflected direction I just computed, but there might still be other obstacles along the way. So I need to trace from that hit position to the deflected position to repeat the process I just did. The thing is, starting a trace from that hit position is likely going to randomly result in a hit right away. And that's because computers store numbers in a limited amount of memory, and so a position is not something infinitely precise. If I zoom in enough, it's almost like a bunch of cells. And so the computer might think the next trace starts colliding with the surface right away. And there's no easy magic solution to avoid this, as far as I know. The easiest workaround is to nudge that trace start position away from the surface hit along the hit normal by some tiny arbitrary amount, enough at least to be safe from floating point precision issues. The thing is, that tiny nudge amount, however small it might be, may very well be just enough to push that position inside another mesh, or the same mesh if it has a weird shape. This has a very low chance of happening, but it may happen, so nudging is not bulletproof, and again I don't think there's a magic solution. I think it's a common issue in past tracers, and I've recently seen an NVIDIA paper with a novel technique to solve this, but it's way above my pay grade. What I did here is extremely silly, but it just illustrates this issue. I traced from the hit position to the nudged position. But remember, I cannot trace right away from the hit position. So the trace itself must start from an already nudged position, so it completely defeats the purpose. But again, I just wanted to illustrate that nudging isn't as innocent as it sounds. Anyway, if that nudged trace results in a hit, I consider this point blocked. Else, everything is good to go for the next trace, so decrease the remaining delta movement by the delta movement that was just applied, and compute the particle's deflected position based on the remaining delta movement and the deflected velocity. Rinse and repeat until either there's no hit anymore, the particle is stalled due to friction, is blocked, or this loop was called too many times. Usually there's some kind of max iteration count to prevent this from firing too many times in case something goes wrong. Cool, so that's collisions, not as easy as it sounds. Moving on, here I apply the obstacle deviation feature. Sounds complicated, but it's actually super simple. I just trace for obstacles way ahead of time based on the particle's velocity. If there's a hit, get the projected direction once again, and compute the deviation force to apply based on that hit time. The closer the hit, the higher the force. Here I compute the repulsion force, similar principle, and next I apply those forces. So deviation is a spherical linear interpolation to deviate the movement direction, and repulsion lowers the speed. It acts as a brake, right? And finally, I compute some sort of overall obstacle deviation value that participates in that turbulence I mentioned earlier during the demo. More on that later on. Next, flow alignment and repulsion. Oh, that one is trickier. This feature again makes a particle react to nearby particles. So this function loops through all simulated paths so far, and for each, gets the nearest point to this particle and performs a distance check to compute two forces. One is an alignment force. Again, this is not physically based at all, but it's all part of an effort to deviate from a rigid body looking simulation. Something that would look more like a bouncing ball than a fluid. I'm trying to convey a sense of flow, so I assumed a particle might be affected by nearby quote-unquote flow and go in the same direction, while also being pushed slightly away from it. That push is a second force and kinda helps prevent points from collapsing onto one single path in concave areas. So here I compute the repulsion force and here the alignment force. It's added to the velocity, but I made the assumption that it would not make the particle go faster than its current speed, for some obscure reasons. And finally, I also compute some kind of overall flow deviation value based on the difference in speed and movement direction to contribute to the turbulence. At that point, I check if the particle has stalled and then continue on with that bit I already explained earlier. If that particle is at one point no longer alive, the path is simulated, and if all paths are simulated, the simulation is ended, and that's where paths are registered. So let's move on to this register path function. First, some context. The user might simulate one path after the other at random positions, right? Maybe one here, one there, one over there, and so on. So that'd be path index 0, 1, 2, 3. The thing is, for that path selection feature to properly work, and for other features as well actually, paths really need to be sorted by their position along that spline, 0, 1, 2, 3. And that's exactly what this register path function does. It just loops through all paths registered so far and compares their position with that new path's own position to know where it should be inserted in the array, if that makes sense. Finally, anytime this register path array is updated, I call this function to enable or disable a few widgets and sanitize a few variables that are dependent on the amount of path, like the debug path index and whatnot. Great, so that's the overall simulation logic. Quite a lot, and actually I'm not even done because I purposely left out quite an important piece of it. Remember this flow deviation feature where a particle might react to nearby particles? Well, this function looks quite innocent, but actually came with tons of challenges, so let's dive into it. To have a particle react to nearby particles, I at first used a naive approach. I used to simulate particles all at the same time and for each particle, loop through all other particles to perform distance checks and compute repulsion forces and whatnot, right? Nothing fancy and nothing too expensive either, assuming there's only a handful of particles being simulated at a time. However, that approach only works as long as particles are all near each other, and due to obstacles, hits, deflections and whatnot, this is likely false. And the idea is again to mimic a fluid behavior, right? So ideally I'd like that particle to deviate a bit when approaching that quote-unquote path. So that method is flawed. A better solution would be not to check where particles are, but where particles were, which is troublesome for many reasons. First, performance is now a huge issue, at least in blueprints. There are thousands of points to loop through multiple times per tick, and it's just too much to use a brute force approach. Second, conceptually, this is still a bit flawed as well, because a particle might then correctly react to a nearby path, but it should also ideally affect it. However, this particle, for instance, could already be way ahead, or even possibly done simulating. So like I'd have to go back in time and simulate it again from that position or something? I suppose it could be done, doesn't sound that complicated for just these two particles, but what if there are 20 though? It sounded like yet another rabbit hole, so I didn't even try. In the end, I couldn't find a solution that pleased me. I suppose I could have done the simulation in Niagara on the GPU and thus kinda solve these issues because it'd be infinitely faster, and then send that data back to the CPU, but then it's a bit annoying to set up in editor and I was already well invested into a blueprint solution, so whatever, I stuck with that method. I just needed some kind of acceleration structure to allow me to query for a path nearest point much faster than the brute force approach. And I opted for a simplified BVH solution. It's still too taxing to generate in real time, so I ended up simulating one particle at a time. Once a first path is simulated, I generate its BVH tree, then I simulate the next particle, which can then get that path closest point and react to it in some ways, right? And so on and so on. So the way I see it, it has two flows. First flow, that second particle cannot influence that first path, it's already done simulating. Second flow, this can lead to weird behaviors when simulating particles sequentially. This first particle may fall straight down, then the second one next to it would probably deviate from it a bit, and then the third one would deviate from the second one, and on, and that would result in this weird deviation pattern. So that's why I chose to simulate particles in a random order. That kinda helps with this issue, but it doesn't really solve it, right? And at one point, if you keep piling up on issues, it's worth asking yourself if this is the right approach. And the simplest solution would be to use Niagara to run an actual fluid simulation. It's definitely a possibility with nowadays GPUs, but it's still quite expensive. Plus, I didn't necessarily want the best looking waterfall ever, I just wanted to try and get the most of this simpler mesh-based technique. And it's always cool to try new things. So for now, this flow deviation feature is as good as it's gonna get. It's not perfect by any means, but it can still help somewhat mimic a fluid behavior, and it was an interesting challenge to solve anyway, so let's have a look at my hacky BVH implementation, shall we? Now, BVH is really popular and there are tons of articles on the subject, so I won't go into too much details here. Plus, I kinda cheated here. It's a much simplified implementation because I made one simple assumption. I assumed a path would pretty much always go from point A to B in a somewhat straight line, despite obstacles, deviations and whatnot, and would never do this. Which meant I could simplify the process of building the BVH tree by simply splitting that simulation point array into two each time. Else I'd probably have to split points along a given axis, and then I'd have to sort points, I think. I'm no expert on BVH honestly, so there are still areas where I'm a little shaky. Anyway, enough rambling, let's take a look at my shenanigans. So it all starts with this find nearest point function, which first calls this build BVH tree if not yet built. And that build BVH tree function essentially simply calls this build BVH node function, which is a recursive function, meaning it calls itself on and on until it no longer has to. And here I assign the first BVH node the entire simulation array. I then loop through all these points to create the overall bounding box and build the first BVH node, that's the root node. Next I compute the amount of simulated points that were sent, so again at first all of them. If that's too many points to quote-unquote contain into one single node, based on an arbitrary threshold, then this BVH node is not a leaf node. So add that node to the BVH tree and create two child nodes by calling this same function twice. And here at first it's like I split the entire simulation array into two. The first node is assigned the upper half and the second the lower half. And because this is a recursive function, this return pin is actually that one. Recursive functions are always a bit of a brain melter. So actually this here returns that root node's index, 0, because it's the first item in that array. And calling this same function a first time here to create its first child node would return 1. And then, well, you'd be tempted to say 2, but no. Because again this is a recursive function, so this first child node is going to create child nodes on its own, on and on, until the algorithm eventually creates leaf nodes. Only then is this called to create that root node's second child node, so its index could very well be 16 or something, I don't know, it depends on the tree depth. So essentially what happens is, for each child node, a bounding box is created for that smaller path section it's been given. Then it checks if the amount of points contained in that section is small enough to consider this node a leaf node. If not, keep splitting and creating child nodes, each time halving the amount of points until that amount is small enough and leaves are created. Leaves then no longer contain child nodes indexes, but the start and end indexes in the simulation array. And that's how I eventually get the data I'm interested in when I'm carrying the BVH tree, that tiny path section each leaf node contains. Voila, that's how the BVH tree is built in a nutshell. I apologize if that's a bit obscure, but I thought it was interesting enough to at least try and shed some light on the process. A BVH tree is all about finding a balance between the amount of data contained in leaves, the amount of data you ultimately need to handle and likely loop through, right, and the tree traversal time. Meaning the more nodes, the smaller the amount of data contained in leaves and the faster you can go through it, but the more expensive it is to traverse the tree in the first place. Thus, the fewer nodes, the faster the traversal time, but the more data stored in leaves, and the more stuff there is to loop through, right? So there's no right answer as to what's best, it depends on the use case. Anyway, that BVH tree construction is a bit expensive to perform in Blueprint, and thus happens only once a path is entirely simulated. Doing it in real time would be way too expensive, I think. Alright, so this BVH tree allows me to query for the nearest point quite efficiently. I just have to perform a couple of point box checks to traverse the tree and only test the few points contained in leaves. And I mean efficiently, but it's a Blueprint implementation, so it's still quite expensive because the Blueprint virtual machine has so much overhead anyway, but it's still way more performant than a brute force approach where I'd have to loop through all these points one by one. Now, the way the BVH tree is carried to return the nearest point isn't that intuitive at first. It's again a recursive function. I pass this function the root node and a nearest distance, which is, at first, set to near infinite. Next, well, that root node is obviously not a leaf node, so I go down there. Here I do a box point distance check to descend into the closest node. And only if that distance is smaller than the smallest distance found so far, which again at first is near infinite, so true, do I proceed forward and go deeper into the tree. At this point, this same function is called again, but I now send that root node's first child node, on and on until the algorithm reaches a leaf node, at which point I loop through the few points this leaf node contains to get the nearest one to the given wall position. Next, get that point's distance to that wall position we're testing, and if smaller than the smallest distance found so far, update that smallest distance. Oh, and that's actually a cool Blueprint feature. See, this nearest distance pin is passed as a reference, so it can be modified from within that function using a setByRef var node. And same with that index. Having set a smallest distance, well, this may be a false positive, so I need to check if the second box distance test is smaller and see if I need to descend into the second child node. It's really counterintuitive at first, but it all has to do with these point-to-box distances, not necessarily meaning this box actually contains the closest point. Like in this example. This point is closest to this box, but it's clearly closest to this point located in that other box. And that's the BVH tree in a nutshell. It's a bit hard to explain, but again it's a well-documented acceleration structure, so feel free to Google if you want more details. Voila, that's the simulation. At this point, you should, hopefully, if I did my job well enough, have a pretty good grasp on how I generate these points and create paths. Now the challenge is to convert them into meshes. Well, time to dig into geometry scripting. So I worked quite hard to build a tool that has a consistent architecture, meaning the way it handles the meshing process is pretty much identical to the simulation process. A generate mesh button is pressed, tool goes into its processing state, Tix then goes through and calls this update mesh function, and depending on the kind of mesh to create, a particular function is called, let's say, update mesh base. In here I get the first pass to process on the stack, process it, and remove it from the stack, and when the stack is empty, the meshing process is done and the tool goes back to idle. So it's quite identical in principle to how the simulation state is handled, right? Clearly the magic happens in that build buffer function. In that function I build several buffers: position, normal, vertex color, UVs and triangles. Once buffers are all constructed, that function is called, and in here, buffers are fed to geometry scripting via its append buffers function to actually create the geometry, and that's it. That's a broad overview of how meshes are generated. Let's dive deeper and take a closer look though. Now, geometry scripting is all in all quite easy to use. Actually, I just released an extensive geometry scripting examples project on my Patreon as a tier 1 reward. It contains tons of examples, some very simple, some quite advanced, so that should be a cool way to get you kickstarted with geometry scripting in case you're not familiar with it yet. Now, geometry scripting offers plenty of ways to create geometry, and what I'm interested in today is the ability to generate any mesh using custom buffers. And the idea is quite simple. First, use a vector array to build a list of xyz positions, that's the list of vertices, and then use an integer array to point to vertices and build triangles. So here the first triangle would be 0, 1, 4, or actually 4, 1, 0. Going clockwise or counterclockwise dictates the normal orientation. Second triangle 5, 4, 1, third triangle 1, 2, 5, then 6, 5, 2, you get the idea. You can also use a second vector array to build a list of normals, one per vertex, a linear color array as well to build vertex colors, and vector2 arrays to build UVs. Feed that to geometry scripting, and voila, you get a mesh. So the sky is the limit really, you can create any mesh you can think of that way. By far the most complicated part of this method is to not screw up the vertex order when building triangles. The best advice I can give you is to use pen and paper. First, make sure you understand the way you build your list of vertices, and then make sure you build triangles with the correct indexes, because it's really easy to make the tiniest mistake here. Alright, so that's the very basics of geometry scripting. Let's see a more concrete example then. Now again, I'm working with a whole bunch of points, right? And the idea is to, from those points, generate, say, that kind of mesh. And the first issue here is that the simulation requires lots of ticks, and thus creates lots of points. Way too much to generate vertices from. So the first order of business is to resample that path. That's fortunately quite easy to do. This simulation point struct contains a distance variable, and when I update the simulation, I simply keep track of the distance traveled. So I know the overall path length, and based on that segment length, I can compute a number of segments and come up with a final segment length. The idea is then to march forward on that path and stop as soon as I march further than this segment length, at which point I can normalize the distance on that segment and know where exactly in between those two simulated points that sample is. So what I called a sample point is really just a struct containing that first simulated point index and how far it is to the next point in a 0 to 1 range. Thus, to sample the actual position, velocity and so on, it's just a matter of doing a linear interpolation between these 2 points. And to make this process more efficient, because I march forward, there's no need to loop through all these simulated points again to get to the next sample. I just need to continue from where I last stopped, if that makes sense. Rinse and repeat on and on until all samples are created, and voila. In blueprints, it translates to this. In this sample path function, I first get the latest sample point to date, because sampling can be spread out over multiple frames, don't worry about it. Next I get how many samples to compute this tick, same mechanism. Then I march forward on that path, just like I explained at first from the first index, to see where the first sample is, meaning as soon as I march too far. I then get that point's index and compute that 0 to 1 interpolation value I just explained, and that's the sample point. Now there's an extra step here. I loop through all points in between 2 samples to check for hit points that may need to be included by force based on this hit threshold. That's this include by force feature. Next loop, continue marching forward from that index on and on until all samples are created. Cool. Having these samples is just one piece of the puzzle though, because it's time to generate a whole lot more data. Positions, velocities, normals, tangents, turbulence and so on. Those are all unique arrays because I built a caching system. Let's assume the user tweaks one of these turbulence settings. Any of those have no effect on the way points are sampled, nor the way positions, velocities and all are computed. Just the way turbulence is computed. So when a turbulence setting is changed, I just invalidate the turbulence cache on all paths. Which means when the tool later asks a path for data to generate vertices from, it calls its cache path function and only if cached goes on, else it waits. And that function goes through all the steps required for the path to be fully cached. So it could very well just need to recompute the turbulence cache, right, if no other was invalidated. Which is quite a nice optimization since this is all done in blueprints and there are quite a few points to process. Now obviously at first a path has no cache at all, so there's a whole bunch of work to do, thus the tool might wait for a while in this state. So first and foremost, samples need to be generated, that's the thing I just explained. Then I build the positions cache. So I'll loop through all these samples and for each one get the position by performing a linear interpolation between these 2 simulated points. It's also here that I include this normal offset feature. So I get the normal, possibly sample a curve with the normalized distance to modulate that offset along the path length and add that offset to the position. Then there's a smoothing path, so it just averages a given position with the previous and next position, rinse and repeat, and that's the smoothing algorithm. Same idea for normals and tangents, there's a smoothing path applied, but first I need to cache them. So to get the tangent, the right vector, I first get the direction between 2 samples. And then I use a cross product with an arbitrary vector that is known to be different from this direction, and that's the tangent. The normal is then just a cross product between the tangent and this direction. Next, distance is just a simple linear interpolation. Flow is a simple linear interpolation as well, but there's a bit more to it. I divide 1 by this interpolated speed, so the greater the speed, the lower this value, and I stack that value on top of the previous flow value. This will hopefully make sense later on once I explain the waterfall shader. Next, turbulence is a bit more complex. It's an average of these hit force, obstacle deviation and flow deviation values. And once it's computed, it needs to be propagated upstream or downstream based on the propagation distance. That gives me a number of points to loop through, both upstream and downstream. And for each point that has at least some turbulence, I loop through points before it for the upstream propagation, compute a fall-off, so the more distant, the less turbulence to add, and do a max operation to propagate that value and not override any existing turbulence, and repeat the same process for the downstream propagation. And finally, the hit force is again just a simple linear interpolation, and that hit force is initially computed during the simulation when I handle collisions, right? So once these caches are all built, I end up with a bunch of points that contain a ton of very useful data to let me build meshes quite easily. An XYZ position, a normal, a tangent, a distance along the path, and so on. And those caches are used in this build mesh buffers function when you already had a glimpse of that build mesh buffers base. That's the one that creates those meshes. And essentially, it's really just a matter of looping through all cached positions, get the tangent at each position, offset that position in that direction and the other way around to create two vertices, and rinse and repeat. Then get the normalized distance to sample a curve and tweak that offset and thus the thickness along the length. I can also create more than 2 points and then sample a curve to offset vertices along the normal and create a bulge. And to create the cross mesh, well, same process pretty much, but switch the tangent with the normal to work on a different axis and voila. So I won't go into too much details here because the video is already long enough, but here basically I sample a curve to drive the thickness along the length using the normalized distance. I then quote-unquote extrude 2 vertices along the tangent vector, apply a line trace if needed, subdivide if needed, and apply the bulge. Next is normal, so it's really just a bunch of spherical lerps based on these settings to select a unit vector. Here's the vertex color, normalized UVs, UVs in centimeters, some more data in more UVs, more on that in a second. And finally, I create triangles. Now there's quite a bit of gymnastics going on here, it'd be hard to explain, and I feel like that's the only real bit here that can really fry your brain. But take your time, feel free to use pen and paper to figure out how the vertex indexes may change based on the amount of subdivisions and whatnot, and you should eventually get it. And again, these buffers are later fed to geometry scripting upon exiting the meshing process to actually build the mesh, right? So yep, that's the base mesh and that's the cross mesh, which is really similar in principle. Building the global mesh, however, is quite different, and I even got 2 different algorithms, like I explained during the demo. And there are complex gymnastics going on here to be able to connect all points of all paths into one single mesh, with cubic interpolation and whatnot involved, and it's so specific at this point that I don't feel like explaining this would have much educational value, so I'll skip over it. However, let's take a quick look at how I generate these meshes. Alright, the idea is to first get those few vertices. Well, easy enough, I just have to reuse the same algorithm used to generate that base mesh, but to only generate the very last segment, if that makes sense. That gives me the vertices in contact with the water, and that creates a path, in a way, right? So next I get the direction from that first point to the next, and I use a cross product with an up vector to get a normal. I can then do a for loop to create a bunch of vertices along that direction and an arbitrary distance. Repeat the process for the next point, on and on, until I reach the end of the path. At this point, I loop around a number of times to rotate around that position, and each time, same idea, I create a bunch of vertices. And the more I rotate, the more I switch from what I call the front radius to the back radius to tell how distant those vertices should be. Once I turn around, I march backward. So, same principle, I get the direction to the next point and use a cross product to get a normal, flipped around this time. Next I spawn a bunch of vertices and repeat on and on until I reach the start of that quote-unquote path. At this point I do a final loop to once more rotate around and connect with the first vertices. And that's the idea. In blueprints it translates to this. I split the algorithm into 2 functions. First I march forward. Each single step of the way I build a list of positions, directions and distances. Then I rotate around the last point. Then I march backward, and finally I rotate around the first point. This is also where I apply the mesh scale. Next I loop through these positions to get the outer perimeter. This is used to create normalized UVs. And then I loop through these arrays to create the mesh buffers, positions, normals, UVs, vertex color, and triangles. Again, there's a bit of gymnastics going on here to build the triangles, but nothing too crazy. And that gives me this kind of mesh. Sweet. Alright, let's take a look at the waterfall shader then, shall we? It's one thing to generate a mesh, but it's not that exciting to look at with UV's default material, isn't it? First of all, I tried quite hard to make translucency work, but translucency is plagued with tons of issues. UE isn't to blame though, the way translucency is rendered in pretty much all game engines is always problematic in one way or another. Biggest issue is sorting, the engine has no easy way to tell what's in front of what. It's a super easy problem to solve for opaque meshes using a depth buffer, but it's a whole different story when it comes to translucency. As far as I know, by default, UE uses the object's origin to sort translucency from back to front, although it's possible to tweak this behavior with this sort priority setting, but it's per actor. So obviously, with one big single mesh, this doesn't solve the issue at all. Now I could split it into multiple meshes, and that most often can help, but it's a bit annoying to do, and may still not even entirely solve the issue. Because the actor's position can only tell so much, right? It doesn't guarantee that triangles doesn't end up in front of another mesh whose position is closer to the camera, if that makes sense. Which is exactly the case here, right? I have these meshes crossing each other, so there's no way to tell what should be rendered in front of what, just by sorting translucency by actors' positions. So I'm kinda stuck with having one big single mesh. And within the same mesh, I believe translucency is sorted by triangles order. Meaning, here I build that mesh using geometry scripting kinda sequentially, right? One path after the other. So those triangles over there are rendered first and those last. Which is problematic, as you can see. That bit here is rendered on top of that part here, despite it being behind. So what was rendered first and what should be in front is quote-unquote overridden with darker values due to the way this mesh here is lit. Now that wouldn't be an issue with an additive translucent material. An addition is order independent, right? 0 plus 1 or 1 plus 0 both equals 1. But with a non-additive translucent material and lighting involved, that's another story. Now UE has this sort triangles option, which does just that. It dynamically sorts triangles by distance to fix this issue, at least on paper. And it seems to somewhat work at first. See, this area is definitely better looking now. But then you look closely at it and you start to see weird things happening. That's because sorting happens per triangle, so that doesn't mean pixels are all individually properly sorted. That's why you get to see some issues still per triangle. Now the more triangles, the more accurate this technique is, I would assume. But then I have no idea what this feature's performance cost is, so it was a dead end for me. There's work done to improve translucency in UE, and lately I think most game engines overall with things like order-independent translucency, but I'm not familiar with that kind of rendering technique at all yet, to be honest, so maybe there's a magic solution I'm not aware of yet, I don't know. Anyway, translucency is also most often expensive, especially if you want lots of shader features like specular, lightning and so on, and even more so when you have quite a lot of overdraw like I have here. There are too many stacked meshes in some areas to afford expensive translucency here, in my opinion. Note that lighting can be calculated per vertex, which drastically improves performance, so that's something to keep in mind, but it has its own drawbacks. Shadow casting is also an obvious issue with translucency, although you can cheat a bit and, for instance, have a translucent material cast shadow as a masked material. Overall, I gave translucency a fair try, but I honestly just failed. You're welcome to give it a spin though, maybe you'll have better luck than me. Anyway, moving on, I remembered at one point this cool tweet by Tim showing early water tests done for Paragon back in the days. He used Dithered masked opacity and it looked quite convincing, so I knew it could look good, I just needed to find the magic trick. Because not gonna lie, by default, Dithered opacity most often looks like a big pixelated mess. Also, switching from translucent to masked opacity made me lose this depth fade feature, which is very handy to prevent harsh clipping. However, there's this good old pixel depth offset trick that can help a bit in that regard with opaque and masked materials. It randomly pushes pixels backward in camera space from frame to frame, and the result is averaged by temporal anti-aliasing, giving that sort of fade-out effect. That being said, this technique causes strong self-shadowing glitches with dynamic shadows, so that's something to be aware of. I'm personally not a fan for that very specific reason. But still, even with that depth of that trick, it looks like complete garbage. So how to go from this to that? Well, there's a magic trick, and that magic trick is called previous frame switch. This essentially lets UE knows what position vertices had the frame before to then make the material output a velocity to the velocity buffer. And I'm no expert, but I'm pretty sure that buffer is used by the temporal anti-aliasing algorithm to try and prevent ghosting and that kind of stuff, not to mention the motion blur, which obviously does make use of the velocity buffer. Now this trick doesn't necessarily need motion blur, it works a bit better with it, sure, but it's not a requirement. This previous frame switch really just allows TAA and TSR to shine even without motion blur, right? Now the way this switch is used is quite simple. You tell UE the world position offset vertices have this frame, so let's say 0, and the offset they had the frame before. Now that previous offset isn't going to offset vertices at all, right? This just allows UE to compute a delta and derive a velocity. So the greater the delta, the greater the motion blur. Let's try -10 in the z-axis. That tells UE vertices all were 10 cm above the frame before, and that results in a downward motion blur. Awesome. So you can literally paint motion blur. The goal now is not to use a fixed arbitrary motion blur direction, but one that matches the way water flows, right? And that can be super easy or super tricky depending on your normals. If you're lucky, you just have to transform a 2D direction from tangent to world space. Tangents by default in UE are computed based on the first UV map, although you can tweak this behavior when computing tangents with geometry scripting. And if you remember, I built that first UV map in a 0 to 1 normalized space. So it looks like this, from top to bottom, left to right. So to get the flow direction, I'm interested in the vertical axis. Well, picture 2D vectors laying flat on that UV space. So that world transform node does just that. It transforms those 2D vectors from tangent space, so relative to the surface, to world space relative to the world origin. And that's how you can get the XYZ flow direction if you're lucky. Why lucky? Well, I failed to understand why, to be honest, but depending on the normals, tangents can be quite funky. See this cross mesh, for instance, its normals are tweaked, so they all point towards that one same direction, right? And for some reason, that seems to screw up tangents quite badly. So this method for getting the XYZ flow direction can work, but isn't a bulletproof solution. Unless I missed something, feel free to let me know in the comments below. So what I did instead is quite simple. I just encode the flow direction in vertex color really. Now vertex color is in a 0 to 1 range, so that unit direction needs to be remapped from a -1 to 1 range to a 0 to 1 range when encoded, and back to a -1 to 1 range when decoded in the shader. But that's it really, that's the flow direction right there. And again, the further the previous offset is, the stronger the motion blur. So I can control that with a parameter to affect how strong this previous frame switch has of an effect. Cool, but rather than specifying a fixed arbitrary value, why not use the actual speed at which water flows? Well, it turns out I also encode the simulation speed in that UV map, so great, get that UV channel, and voila. That motion blur's intensity is now based on how fast water actually flows. Awesome. Now let's investigate the rest of the shader, cause there's a bit more to it. On top of that trick I just explained, I offset vertices in two different ways, sideways and forward. First, this bit simply creates a sine wave scrolled along the first UV map. It's used to control the push amount along the vertex normal, flattened in X and Y, to prevent vertices from being pushed in Z, which could be an issue at the water level. But also controls the sideways offset. Now remember, this second UV map contains coordinates in centimeters, right? If that mesh is say 100 cm thick, that vertex UV would be -50 cm in the U-axis, and that one +50. And using the same tangent to world space transform I explained a minute ago, I can convert that 2D direction into an XYZ direction, which magnitude is based on the mesh thickness. The thinner, the smaller the offset. And that, in my opinion, adds quite a bit to the overall effect. It gives the impression of a varying water flow, something that looks a bit more random and lively, right? Cool, so that's the world position offset. Now using a subsurface material might help to smooth out shadows, something to try. It's one of the downsides of using a masked material, shadows are quite harsh. There I used a plain color, super simple. Material is fully rough to make it a bit cheaper. For the opacity mask, I used a custom flipbook texture. I just googled royalty-free waterfall photos and copy-pasted random bits here and there to create these 4 separate waterfall textures that tile vertically. And also I have a similar texture, but one that looks a bit more splashy, I guess. One is stored in the red channel and one in the green channel. And the way this texture is sampled is quite interesting. It packs a few neat tricks, but nothing too crazy. So this is a rework node, right? So it comes from there, so let's investigate this bit first. I first construct UVs, so that's the U-axis and V-axis. I use time to offset the v-axis and thus scroll the texture vertically, right? It's also offset with this seed value I encoded in UVs right here. And that seed variable again is a variable exposed on spawn in that actor, variable set when the path is created. That way a path is assigned a random 0 to 1 value I can then retrieve at any time. That simply ensures that a mesh doesn't scroll that texture from the same position the mesh next to it does, and the texture pattern can be quite apparent and off-putting. Now the u-axis is just this normalized 0 to 1 value. The v-axis, however, doesn't come from this first UV map, but from the third one. That's where I encoded that flow value. The faster the water flows, the less UV space, resulting in stretching, which, when scrolling a texture, further helps sell the idea of acceleration and momentum, right? Finally, I once again use that seed value to randomly shift UVs along the u-axis and have each mesh randomly select one of these 4 textures. Cool, so that texture is sampled and its red and green channels are lerped based on that speed value stored in UVs. That's to mimic this typical waterfall loop, where it's kinda splashy at first and then the water turns into mist as it gains speed. So I can control the speed threshold at which the opacity is lerped between the splashy looking texture and the more misty looking texture, if that makes sense. And that's pretty much it. Now that material as is wouldn't work at all on any other mesh, right? It's designed with this geometry scripting generated mesh in mind because of the amount of very useful data I encode in UVs and vertex color. So in the end, this shader is nothing too complicated overall. It's super duper cheap for how good it can look in my opinion, but it has a few motion blur and temporal related glitches. Nothing's perfect, especially water. It's an incredibly hard thing to tackle in real-time rendering, and this again is by no means the only way to create a decent looking waterfall. It's just one of the many different methods. One other technique I'm really interested in trying is scrolling an actual mesh with some kind of world position offset shenanigan. It would help give the waterfall way more volume, cause it's one of my technique's weakness. It can look a bit flat and lack some volume, and using an actual splash mesh could be a cool alternative to try. Plus it would allow me to give translucency another try, especially because with such technique, overdraw is much less of a concern. So yep, something to try at one point. Alright, time to talk about the particle system that is not a particle system. How do these particles work? Well, let's start simple. Here's a quad. It's at 0, 0, 0 in world space and has a simple material applied to it. Let's create a simple time loop that goes from 0 to say 1.5 seconds. And then normalize it to a 0 to 1 range as well. Cool, let's use this time loop to offset vertices in Z by some amount. Okay, that's a linear motion though, not super interesting. Let's create a gravity accelerated movement instead. Super complicated. Nope, kidding, it's not. Time loop squared multiplied by gravity multiplied by 0.5. That's it. Now let's add some initial vertical velocity. Super simple as well. Add the time loop multiplied by some speed in centimeters per second and done. That's kinda cool already. What about an initial velocity in xyz? Well, simple enough. Add the time loop multiplied by some speed in xyz in centimeters per second and done. Nice. Now the challenge is to hide this loop, maybe have some kind of fade in and out or scale in and out or both. Let's try a fade in and out first, so switch this material from opaque to translucent, use the normalized time loop to create a bilinear gradient and voila. The opacity goes from 0 to 1 back to 0 right when time loops on itself. I can then use a power to control the speed at which the fade happens, or sample a curve atlas to have control over the opacity over time, just like in Niagara. What about a scale in and out? Well, that's a bit more complex, but nothing to worry about. First, let's collapse all vertices to the world origin. Next, add the actor's position back to all vertices, and then their initial local position as well. Cool, I'm back to square one. However, now I can scale that initial local position. Thus, I can use that bilinear gradient I used on the opacity on that scale as well. Cool. I can even take it a step further and create a billboard particle. Simple enough, transform that initial position from view space to world space. Oh, it disappeared. Well, that's to be expected. For this simple trick to work, this mesh needs to point towards -z. By the way, I've covered this kind of world position offset tricks extensively in many of my previous videos, especially in my stylized grass video, so I'm going a bit fast here. Anyway, so switch to a quad that faces -z, and voila, it now faces the camera. So you kinda see my point already, right? You can quite easily recreate very basic ballistic motions with shaders. However, the trouble begins when you try to apply this on a mesh that has many quads to create lots of particles, right? It all breaks apart because this mesh has one single pivot point, and that world position offset logic operates around that single pivot point. So the idea is to somehow store each quad's offset from the actor's origin to then have that world position offset logic work around each quad's own pivot point. How so? Well, UVs. And thanks to geometry scripting, it's super straightforward to do. Encode each particle's XY position in UV1 and the Z position in UV2. Then reconstruct that XYZ position in the material graph, subtract that offset from the initial vertex position, and replace this actor position node with pivots converted from local to world space. And voila, quite neat. We can even go one step further and help TAA and TSR and add motion blur. And this again is done using this previous frame switch. And the most simple solution is to duplicate this, subtract delta time from time, and done. That's the offset this particle had the frame before. So plug that in there, maybe switch the material to opaque to better see the motion blur in effect, and while we're at it, fix the normals with, say, for now, a vector pointing towards the camera in world space, and voila. Let's try something else. The difference between these two offsets can be used to derive a movement delta, which can then be normalized to compute a movement direction. And that movement direction can be used to replace that simple billboard logic with a camera-facing, velocity-aligned particle. Neat. Now, there are still a few issues, obviously. First, all these particles are synced. Second, they all go in the same direction and have the same speed. Well, to solve the first issue, I encode a random value in the vertex color alpha channel and use it to shift time randomly per particle. Now, what about the movement direction and speed? Well, let's again make use of vertex color and UV channels. So let's encode the movement direction in vertex color and speed in UVs. And that's it, that's the idea. So the challenge now is to spawn these quads along each path. But actually that's not so different from how I generate these other meshes. I use the same caching system and sampling technique to get a bunch of positions, normals and tangents along each path, and for each position add a quote-unquote particle to those buffers, so really just 4 vertices, 2 triangles and the corresponding normals, vertex color and UVs, in which I encode a bunch of data like I just explained. Finally feed those buffers to geometry scripting and done. There's however one feature that complicated it all, and oof, it made me go nuts. You see, at first, the way I applied these filters was quite naive. For each sample, I checked each condition, and if one failed, the particle was skipped. So you could ask for 20 particles and end up with one somewhere on the path if that one sample happened to match those criteria, if that makes sense. So not a great user experience. I'd like to have 20 particles spawned if I ask for 20, right? So I had to go for a different approach, and I came up with what I called regions. A region is defined by a start and end point, and a 0 to an alpha for that start and end point. If that start alpha is not 0, it means that region actually starts in between these 2 points. Same for the end alpha. So a first filter by, let's say, distance can create this very precise quote-unquote region. A second filter might then be applied on top of that region to possibly further shrink it. And multiple regions could be created because of, say, a heat filter, right? There might be multiple but scattered points along that region matching this heat filter. A huge pain in the butt to solve. For some reason, my brain was not cooperating with me at all on this issue, but I got it done. So that system allows me to sample a bunch of points along those regions and spawn the correct amount of particles, all correctly spread out. Now, the actual algorithm is in principle quite similar to the sampling algorithm I explained earlier, the one where I march forward to know where a sample is, yeah? And that quote-unquote sample triggers the start of a region, and then I continue marching forward until I march too far, and that's the end of the region. However, in Blueprint it's not as elegant, because filters can be stacked, and so each filter needs to march not on the quote-unquote simulation, but on regions. So I need to handle the start and end interpolated points, and it makes the algorithm not so easy to explain. Plus, I had to come up with two different algorithms to also handle specific values like hit force and turbulence, so a given point might meet a min and max threshold, and based on the closest threshold, checks the previous and next point to see how far the region can extend from it. Again, a huge pain in the butt to solve. Sometimes having to deal with huge graphs and tons of nodes goes against you when tackling a complex issue. It'd be so much easier to do in C++. Blueprint has its limits for sure. Not to mention that sometimes you can just brute force something in C++ and not have to worry about performance so much, and that can be a lifesaver. One more thing worth explaining is this FX baking tool. So again, this lets me bake a bunch of positions and velocities into two textures I can then sample in Niagara to spawn particles, right? Turns out this was quite easy to do because I worked quite hard to build a decent and scalable architecture. That was the hard part. Once I had the tools to extract a whole bunch of information from those paths and the simulation, then adding a feature could be a matter of mere minutes. And for that feature, I again used that caching and sampling system to, well, sample a bunch of positions and velocities. And I write each position into a render target and each velocity into one as well, and that's essentially it. Each render target can then be converted into a static texture, and a Niagara actor can then be spawned and tweaked to make use of these static textures, like so, and voila. Now, the way I sample these textures in Niagara is quite simple. It's done in a custom module here. I get the texture's dimensions and generate a random texel position, I might say. The thing to keep in mind here is that these samples are packed in this texture in that way, sequentially, one after the other. So that pixel here could be the end of a path, and that one next to it the start of another path. And the main thing to avoid here is sampling in between those two pixels. That would essentially average those two positions and thus spawn a particle at an invalid position, if that makes sense. Hence why, with this bit of math, I generate random fixed point UVs. UVs then used to sample the first texture, the position texture, and the second one, the velocity texture. Those values are output parameters, so they can be accessed from outside this custom module, in the same stack it's placed on. So in my case, anywhere in the particle spawn stack, after the module obviously. Like here to set the particle's position, and here to set its initial velocity. And that's the gist of it. The rest is not really important, it looks like garbage anyway, because again this really wasn't my priority, and it's really just a template for you to get started with this method if you so desire. Very last topic I want to cover, the water shader. Having a cool looking waterfall is one thing, but if it ends up in water, it has to blend well with it, right? And so the water shader can play quite a big role in the overall look, especially to help beautify that whole splash zone area. Here's an example. This water shader isn't particularly complex nor interesting, but it makes use of a flow map, and I wanted to explain how I made it. Because flow maps can actually be really easy to create if you know a couple of tricks. So first I exported this waterfall mesh to FBX and imported it into Blender. Next I duplicated the water mesh and subdivided it a couple of times. Then I simply move these vertices up like so. And that's basically it. There's a flow map right there embedded in the geometry. And to get it, well, you bake a normal map. Now, normal maps are usually baked in tangent space, meaning relative to a surface. And when that surface is a world-aligned flat geometry, that tangent space is actually world space. Which means I don't even have to bake a tangent space normal map like you'd normally do. Instead, I can literally output that geometry's world normal remapped to a 0 to 1 space to have that x and y slope, and that's the flow map. And the reason I do it this way, instead of using Blender's bake feature, is so that I can also pack a height map in the blue channel all in one go. Else I'd probably have to bake a normal map, save it, edit it, get rid of its blue channel, replace it with another image, quite tedious. And so to quote-unquote bake a height map, I added a cube, scaled it to match that mesh's height, and used that cube's object, the coordinates. Quite an important note, at this point it's probably important to work in linear space. Next, I baked that mesh's emissive material onto that unmodified flat mesh, exported the image in linear color space, 16 bits as well, super important, and voila, that's the flow map in the red and green channels, and the blue channel can be used as a distance gradient to fade out foam and whatnot. Now I guess this could even be done in editor, but that probably wouldn't be straightforward to implement, and I can't afford further work on that tool. Time to call it done and move on. Anyway, the water shader itself is nothing to brag about. It's quite ugly on its own. I merely wanted to beautify that splash zone, so I didn't spend a lot of time on this shader. The flow map is used to sample a foam mask and foam normal map, but also a wave normal map. And to create that foam texture, I again googled free photos, copy-pasted random bits here and there to create a tiling texture. Then that flow mask is used to make the water opaque, tweak the normals, specular and roughness, and the rest is pretty standard if you ever use the single layer water shader model. Now here I sample the distance gradient, the texture's blue channel, with some kind of bump offset to lerp some water attributes and give the impression of an underwater layer, like bubbles and whatnot. It's pretty dull to be honest, but hey, this is a waterfall video, not a water video, okay? That's it, I think I'm done. I think I've covered most of what there is to know about this tool, and I hope I gave you a sense of what it takes to create this kind of custom tool. It's quite a bit of an effort, to be honest, but it's incredibly rewarding. Now, there are a few details I didn't mention, and as usual, the devil lies in the details. I could, for instance, mention the freeze function, and I at first used geometry scripting's polygroups to do that, but it added so much complexity. So I ended up going with a single actor per mesh, and freezing a mesh is just a matter of adding the quote-unquote current mesh the user is working on onto a stack, and then clearing the actual mesh reference. That way the tool no longer thinks it needs to clear a mesh before regenerating it. But it still has a way to point to those frozen meshes when needed, like when compiling them all to create one single unified static mesh. Alright, that's the end of the video. I certainly hope you learned a few things. If not, I at least hope it was entertaining. I would appreciate a like and a subscribe if you did like the video. Would be cool to reach 10k subs for New Year's Eve. Anyway, this tool is available as a tier 3 reward on my Patreon, along with many other great educational UE projects and demos. I also released a simplified version of this custom physics simulation I built for this waterfall tool as a tier 1 reward. It features a few extra neat techniques like interpolated spawning and such, so worth taking a look into. I also released that hacky Deviation implementation of mine with a debug view and whatnot. It's so cool to see it functioning in real time. And this is a tier 1 reward as well. I also released quite an extensive geometry scripting content example, very valuable in my opinion, tier 1 reward as well. And finally, I also very recently released a fun way to make use of geometry scripting. It's available as a tier 2 reward in case you want to slice tomatoes. Voila, that's the end of the video. Thanks so much for watching and thanks so much for your support. Massive shout out to all my Patreon supporters. I apologize for the delay. This project took me way too long to complete, but oh well, that's how it goes sometimes. Let's stick to simpler things for the next few projects and get back to more frequent releases though. Alright, thanks again for watching, I'll see you in the next video, take care of yourself, bye bye!